See what is an impulse response and a mathematical operation called convolution. So let us start with impulse response. So impulse response for a continuous system will be denoted by h of t, and for discrete it will be denoted as h of n. So let me explain everything in terms of h of t. The case will be similar for a discrete system. So this is you can say it is an identity of an LTI system, a linear time invariant system. So for an LTI system, there is a parameter called h of t. So this is a parameter, or this describes the system characteristics. So this behavior of, you know that for an LTI system, the behavior of system is time invariant. So it's always a constant. You can say behavior is not varying. So whenever you give x of t as input, say you will get y of t as output, right? So this is independent of the time. For any time when you give x of t, you will get y of t. So for such LTI systems, you can define a system identity called impulse response that will be denoted by h of t in continuous domain. Now another use of impulse response is that using an operator called convolution, you can find the output. So I will explain convolution operator also here, and we will continue discussing about little bit about impulse response, and we will focus mainly on convolution. So just to introduce convolution, it is a mathematical operator that relates input and output of a system. So if you know the input of a system, and if you know the say impulse response h of t, then you can calculate y of t using this particular operator. So in continuous domain, we call it as convolution integral, and it will be denoted with this symbol, asterisk symbol. So y of t will be, we will read it like this: y of t is equal to x of t convolution h of t. So convolution is a mathematical operator that help you to find the output of a system when you know the impulse response. Now let me stick on to few things about impulse response. When you speak about impulse response, we have seen about system stability during the last class. That was about Bibo stability of a system. Okay, Bibo stability. So that was bounded input, bounded output stability. So in that case of Bibo stability, what we did was, if your input signal is bounded and if you are getting a bounded output, you can say that the system is stable. That was the methodology that we used. Now I say that looking at h of t, looking at the impulse response h of t, you can say the stability of the system. So even causality can also be calculated. Now let me give you a few examples where we can calculate the stability from h of t. So this is the method that you have to use in order to check stability from h of t. What you have to do is, if you after learning convolution only you can prove it, but I will just give you the condition. Okay, so if integral minus infinity to plus infinity mod h of t dt, you can say h of t dt, if this value is less than infinity, that means if it is absolutely integrable, if your h of t is absolutely integrable, then you can say that the system will be stable. So if this condition is satisfied, you can say that the system will be stable. So this is how you can check for stability using impulse response. For example, let us consider a few systems. Say for example h of t, first one, say h of t is equal to e raised to 2t into u of t minus 1. So if you look at this system, if you integrate it, e raised to 2t u of t minus 1, this will not be a finite value. Okay, you can continue with the mathematical part, but I am not going into that. I will just look at this particular signal and say whether it is stable or not. Because looking at h of t, you can say that, see, e raised to 2t, you know that the graph of e raised to 2t is like this. So when you multiply with u of t minus 1, so 1 comes over here. So you will have a system like this. You will not, I will highlight in another color. Say your h of t will be like this white colored area. So you can see that the area under this curve is infinity because it is going to infinity. So it's not a finite value. So you can conclude that the given system is not stable. So this is not stable system. So you can check this mathematically also, but I am approaching it graphically. Then second thing, let's consider another example. Say h of t is equal to e raised to minus 2t. Okay, e raised to minus 2t into u of t minus 1. So we know that e raised to minus 2t, the graph will be decreasing exponential. So e raised to minus 2t graph will be like this. And when you look at e raised to minus tt into u of t minus 1, so this is 0.1. So your graph will be like this white colored region, right? So this will be e raised to minus 2t into u of t minus 1. So you can see that the area under this graph is a finite value. This point is 1. So it's a finite value, will be a finite value. It's approaching 0. But when t equal to infinity, when t is equal to infinity, you can say that this value is 0. So it's a finite area. So when h of t is absolutely integrable, integral of a waveform means the area under the curve, right? So when it is absolutely integrable, you can say that system is stable. So the second example we have given is a stable system. Stable system. So you can do this calculation just or you can say whether a system is stable or not just simply looking into your impulse response. That is one another use of impulse response. Like similarly you can check for causality also, go through that. So let me move on directly to the convolution part. So the next part is to discuss about the operator called convolution. So as I mentioned earlier, convolution operator will help you to find the output of a system if you know the impulse response. Say y of t is the input, convolution, the impulse response h of t. So that is the equation that you have to use. So mathematically it is defined like this: integral minus infinity to infinity x of tau h of t minus tau d tau. So this is the expression which we have to this is how convolution operator is defined. Integral minus infinity to infinity, we call it as convolution integral because we have convolution in continuous domain as well as in discrete cases. So in continuous case we call it as we will use the symbol integration, and discrete that will be summation operation. So here we always call it as a convolution integral. So integral once again y of t is integral minus infinity to infinity x of tau h of t minus tau d tau. This is the equation that you have to use to solve the problems or just to find the output of a system, provided when you know the input as well as the impulse response. So let's see some properties of impulse response first. Properties. So the first property is these are not properties of impulse response, properties of convolution. We look at some properties of convolution operation. So first property is commutative property. So in convolution is a commutative operator, you can say. So it's a mathematical operator. So you can say x1 of t, let's consider two signals, x1 of t convolution, x2 of t. x1 of t convolution, x2 of t will be same as x2 of t convolution, x1 of t. We can change the order, that's it. That is the meaning of commutative property. Second one is distributive property. So as any mathematical operator, this convolution operator is also distributive. That is, if you have say x1 of t convolution of consider another two signals, say x2 of t plus x3 of t. If you have something like this, you can open the bracket, it's distributive. So you can find x1 of t convolution, x2 of t, right? You can perform this, then plus you can multiply x1 of t or perform convolution. It's not multiplication, it is convolution. x1 of t convolution, x3 of t. Okay, so this is possible. So that is distributive property. Third one is associative property. That means if you have say three convolutions, x1 of t, three signals, x1 of t, x2 of t and x3 of t, and say you have to perform convolution between these three. So you can perform it in any order. You can perform it in any order. Say you can perform x1 of t convolution x2 of t first, then you can convolve with x3 of t, or you can perform any of this. Say I can perform x2 of t convolution x3 of t first, let me mention it in brackets, then you can convolve it with x1 of t. So that is associative property. Fourth one is shift property. Shift property. Say in this case, if you consider two signals, say x1 of t convolution x2 of t, say the result is y of t, assume that the result is y of t. Now if you perform a convolution of a shifted signal, say one signal is shifted by t units minus, say t minus t, then your output will also be a shifted version by the same parameter. Shift parameter will be same. That is a shift property. Fifth one, this might be very much useful many times. Say convolution with impulse. Okay, convolution with impulse. Sometimes you may have to perform convolution of a signal with the impulse signal, that is x of t. A signal has to be convolved with, say, del of t. You know that del of t is the impulse signal. So that will be always x of t itself. That will be x of t itself. You can verify that here. Say you can prove it. I will just simply go through the proof of this. Say x of t convolution del of t. So how will you perform the convolution operation? Convolution x of t convolution del of t. So mathematically it is defined as integral minus infinity to infinity first signal, that is x of tau, into second signal h of t minus tau. This is how it is defined. Now in our case it is not h, what we have is del. So let me delete h and let me write del. So del of t minus tau d tau. So do remember one thing here, your axis is actually tau instead of x of t. The signal is not x of t now, you call it as x of tau. Okay, you have x of tau and say del of tau, but here you have del of t minus tau. So where t is something like a constant parameter, here the variable your independent axis is not t but it is tau. Okay, now look at this mathematically. So we know that del of t minus tau, del of t minus tau means this is, say, del of tau will look like this. Del of tau, this is tau, del of tau will be like this. At 0 only it is defined, right? So del of t minus tau means you have to mirror it and shift by parameter of t. You can verify that mathematically later. So this is how the signal will look like. Okay, this is how the signal del of, say, t minus tau be like. So a shifted version, shift parameter is t units. If you take minus outside, you will have minus of t plus tau, sorry, minus of tau minus t, minus of tau minus t. That's what I have drawn here. Okay, that's why I have made it right shifted. So anyway, whatever it is defined only at the point t. Your del of t minus tau is defined only at the point t. So my conclusion is, the signal when you multiply with x of tau will be distributed in the tau axis, but whatever the values in the other region, that doesn't matter, because this particular signal del of t minus tau is defined only at t. So if you have confusion, I will just write this signal once again like this. Tau is your independent axis, so you can write it like this, del of minus of tau minus t. So how will you do this? First you have to perform reversal. So del of minus t and minus tau and plus tau, that doesn't make any difference. So even though you perform reversal, it will be like this only. Then you have to shift it by a factor of t. It is minus t. So you have to right shift. You have to right shift the signal. That's how it looks like this. Okay. Now I'm going to delete it. Now come back to this. Let's focus on this integration. So this integration minus infinity to plus infinity, x of t is enough because it's defined only at t. Now del of t minus tau d tau, right? So if you look at this expression, you can say that area under the curve, x of t will be, say, a constant value. You can take it outside, right? You You can write it outside. Then minus infinity to infinity del of t minus tau. I am taking x of t outside. My variable is tau. It is not t. T will be a constant value. Okay, don't get confused. While dealing with convolution, we are renaming the independent axis, time axis t with tau. So this is, you can see over here, it's d tau. So that's why I took x of t outside. You cannot take x of tau outside the integration, but you can take x of t outside the integration. So this is simply x of t into, this is area under the impulse, that will be 1. Area under impulse will be 1. So you can say that this is equal to the RHS x of t. So you can see that the integration convolution with del of t, your result will be simply x of t. So that's all about convolution with impulse. Now the last one, say the last one is width property. This will be very useful when we deal with problems. Width property. Width property. Say if you have two signals x1 of t, so you are going to perform convolution with say x2 of t. Say the result is y of t. Result is y of t. So if the duration of the signal is say t1 and the second signal duration is t2, then the convolution result will have a duration of t1 plus t2. So you can see that signal length this will be increasing. So if you have t1 time period, assume that time period of this particular signal x1 of t is t1, or the duration is t1. And for the signal, if the duration is t2, when you perform convolution, the duration will be the sum actually, t1 plus t2. So that's all about basic properties. And some more additional things when we speak about convolution is that, or we'll look at the problems first. We'll look few problems. So problems related to convolution integral can be do in two ways. Okay, so how to solve convolution? Let's see how we can solve convolution operation. So when you want to solve a convolution, say x1 of t, convolution x2 of t, you can do it in two ways. Convolution integral can be done in two ways. One is you can use the direct equation. Okay, you can use the direct equation. Second method is graphical method. So we'll see both the methods. So let us start with the direct equation. First we will start with direct equation. We will be going to use direct equation of convolution to calculate the output of an system. So let's try with a few examples. So the first question is we may take few example questions. Let us consider an example. So let's consider a system where the impulse response is say h of t, and you have an input x of t and the output is y of t. Say the h of t is given by u of t. Okay, your h of t is defined as u of t, and say the input x of t, your input x of t is given by t into u of t. Let's start with some simple problems. So let's see the solution. So how can you find the output y of t? So in order to find the output y of t, what you need is you have to perform convolution between input and output. So you have to perform convolution between the input x of t with the impulse response h of t. So x of t is t into u of t. It's given like that. You have to perform convolution with u of t. So we know that the equation is integral minus infinity to infinity x of tau. I'm converting everything in tau. X of tau into h of t minus tau d tau. Okay, now focus carefully. Integral minus infinity to infinity x of tau. X of tau is, x of t was t into u of t. So x of tau will be what? Tau into u of tau. Into now h of t minus tau. So h of t was u of t. So h of t minus tau is u of t minus tau d tau. So you have some u of tau, and your variable axis, independent axis is tau. So you have u of tau and u of t minus tau. So what is u of tau? Let's find the signal. u of tau. U of tau expands only from 0 to infinity, you know that. So you can make the limit as 0 to infinity tau into u of t minus tau d tau. Right. Now let's try to plot the signal u of t minus tau. So that will be done in 2-3 steps. So this is u of tau. You know that u of tau is a step signal. So u of tau will be like this. This is u of tau. Now I need u of t minus tau. So what all things you have to do? Once again I will show this operation. U of t minus tau is the thing I need to plot. So this is u of minus of tau minus t. Sorry, u of minus of tau minus t. So you have to perform reversal first. So when u of tau is reversed, you will get u of minus tau, right? So you have to perform reversal. I am trying to plot the signal u of minus of tau minus t. So you have to perform reversal first. When you perform reversal, it will be like this, right? Now you have to right shift it by t units. So the signal will be right shifted to t units. So this is the second signal. So where it spans from minus infinity to, this spans from minus infinity to t. So you can say that our integral 0 to infinity will be now from 0 to t only. Okay, 0 to t only. So when you multiply these two signals, first signal was u of tau. Okay, first signal was u of tau. So when you multiply these two signal, I will have the signal from the span 0 to t only, 0 to t. That's why the integration is from 0 to t. You can directly do in single step also. So 0 to tau t tau d tau. Now when you integrate it, you will have integral of tau is tau square by 2, and integration limit is 0 to t. So you will have, say, t square by 2 minus 0. So the answer is t square by 2. So always you will have you can say into u of t. So this is your signal. This is your output signal y of t. So using convolution operator, you have calculated the output. See, whenever the input is t into u of t, and whenever the impulse response is h of t, we found that the output will be what? T square by 2 into u of t. So this is the use of convolution operator. We will see a few more examples. Next question. Find the output of a system. Find the output of a system when the input is e raised to minus at into u of t, e raised to minus at into u of t, and the impulse response of the system is, say, e raised to or say e raised to minus bt into u of t. We'll choose some general case, e raised to minus bt into u of t. So he is asking me to find the output of a system. So definitely you can go for convolution operation. So y of t, the output is simply convolution of input, okay, e raised to minus at into u of t, convolution e raised to minus bt, this is the impulse response, into u of t. So you perform mathematically the convolution between these two signals, you will get the output. So it's integral minus infinity to plus infinity. So you will have x of tau. I am directly writing the tau version, x of tau. So e raised to minus a tau into u of tau. This is x of tau into, this is h of t. So you need h of t minus tau, right? So e raised to minus b into, you can simply replace t with t minus tau into u of t minus tau d tau. So integration limit, again it's similar to the previous case, u of t into, you have to multiply these things. U of t signal, it spans from 0 to infinity, you know that, 0 to infinity, and this one, it spans from minus infinity to say t, minus infinity to t. So when you multiply these two signals, you can say that the integration limit is from 0 to t, 0 to t. So at 0 to t you will have e raised to minus a, say a tau, here you have minus b t minus tau. So you can take tau outside, or let me open the bracket first. E raised to minus a tau into e raised to minus bt into e raised to minus, plus b tau d tau. So you have a constant term in this, right? E raised to minus bt is constant. Okay, t will be a constant value. I repeat, t will not be your independent variable. Your independent variable is tau. T will be a constant value. So you will have e raised to minus a tau into e raised to b tau. So if you take a minus outside, you will have, say, you can write it like this, say a minus b into tau d tau. Now you can perform simple integration and you will get the result. So just integrate it and substitute upper limit and lower limit, and you will end up with something like this, e raised to minus at minus e raised to minus bt. You will have a minus b f minus, so it will be b minus a into u of t. So this will be your final signal. I have skipped the integration step. You just integrate it, e raised to minus of a minus b divided by a minus b, and substitute 0 to t. Okay, so this will be the final answer for you. So this is how you can directly solve the convolution operation using the mathematical equation. That is, once again, integral minus infinity to infinity x of tau into h of t minus tau. Now let us see how we can solve this graphically. So the second method is graphical method. So we are going to look at the graphical method to solve convolution integral. Okay, I repeat, you are going to look at the graphical method to solve convolution integral. So I will explain the graphical method using an example. So let's consider one question. So assume that you have to perform convolution between, say, x of t, this is your input, that is, say, e raised to minus 2t into u of t. Okay, and you have the impulse response, say, h of t. Impulse response h of t is u of t plus 2. So let's find y of t, that is x of t convolution h of t. So this is the thing you have to do. So let's look at the method. So it's a graphical method, so you should be aware of the shape of x of t and h of t. Let me draw that. So you know that the expression the direct mathematical equation, we have x of tau and h of t minus tau. So here also I'm going to convert your input in the tau axis, name of tau. So you will draw x of tau first. X of tau is e raised to minus 2t into u of t. Hope you are able to draw this directly. Signal will look like this, something like this. E raised to minus 2t comes like this. It's a decreasing exponential, but you have only the positive side. You have only positive side because I have multiplied e raised to minus 2t with the u of t. So this is x of tau. So what we need is actually two waveforms. Okay, first step is to plot two waveforms. One is x of tau. The second one that I need to plot is, what I need is actually h of, as per the equation, as per the convolution integral equation, we know that it is integral of x of tau into, you have to multiply it with the second signal. So that is h of t minus tau. This is what you need. So let me try to plot that. So let me plot h of t first. Okay, let me plot h of t. I will plot in another color. So this is h of t. Let me mention it in terms of tau first, h of tau. So what is h of tau? U of tau plus 2. So u of t is from 0 to infinity. So plus 2 means you are to left shift. So you have to start from minus 2. So this signal spans from minus 2 to infinity, right? So that is your h of tau. So what I need is h of t minus tau, right? What I need is h of t minus tau. So as we mentioned earlier, again h of t minus tau is, you can take minus outside. So this will be h of minus of tau minus t. So you have to perform reversal first. So you have to perform reversal. So when you perform reversal, what you will get? The signal will be like this. When we perform reversal, signal will be like this. That means taking mirror of the signal about the say y-axis. So this point will be say 2. Okay, this point will be 2. Then you have to shift it by t units. Small t units shift. Right shift by 2 t units means it will be 2 plus t. This point will be 2 plus t. So this is the signal h of t minus tau. Now let me mark it in white color itself. So these are the graphs that I need. Okay, I need to multiply these white colored graphs. So in order to perform this multiplication result will definitely depends on the value of t. Depending on the position of t, it will change. So consider a case like this. Let me mark your x of tau. This is your x of tau. Okay, this is your x of tau. And let me place your h of tau over here. Okay. Your h of tau will be like this. So this point is 2 plus t. What I'm going to try is I'm going to slide this waveform. Okay, I'm going to slide this particular waveform from left to right. See, if we keep like this, that means you'll have different cases. See, when this is the first case, let me write it as case 1. So when 2 plus t is less than 0. Okay, when 2 plus t is less than 0, that means when t less than minus 2. When you take this to the right, it will be like this. So when t less than minus 2, when the value of t is less than minus 2, both graphs will be like this. See, say this is number 1 and this is number 2, graph number 1 and 2. So when you multiply 1 and 2, what will be the result? Your y of t will be, the y of t is actually integral minus infinity to infinity product of first waveform into second waveform, d tau, right? So when you multiply these two, we can say that the product will be 0 because there is no common region for 1 and 2. So product will be 0. So this is say case 1. This is case 1. Similarly, we have to look at the next case. So we are actually sliding the waveform, second waveform over the first one. So whenever you cross 0, so case 2 you can define it like this. So when say 2 plus t is greater than 0, I think there is only 2 cases over here. Okay, whenever it is greater than 0, you have one single one more product will be there. So I will draw that separately over here. When it is greater than 0, it may look like this. This is your first waveform. Second waveform will be like this. Okay, so you can say that this point 2 is 2 plus t, that is greater than 0. That point is greater than 0. Now what will be the product? The product will be this region. That means how can you calculate it mathematically? Say y of t, how can you calculate this green colored region over here? Its integral, lower limit is 0, upper limit is 2 plus t, integral 0 to 2 plus t. What is your wave amplitude? First one into second one. So first one is e raised to minus 2t into, what is the second one? U of t, its value is 1, d tau. Okay, you can say it's not t raised to minus, it is not e raised to minus 2t, it is e raised to minus 2 tau. We have converted the axis to tau. This axis is tau. Now when you perform the integration, you will get that particular result. So let me integrate it. So integral e raised to minus 2 tau is e raised to minus 2 tau divided by minus 2, and integration limit is 0 to 2 plus t. 0 to 2 plus t. So when you substitute this value, what was the case over here? You will get the value of y of t for t greater than minus 2. So we have seen that for t less than minus 2, the function value was 0. Now for t greater than minus 2, let us check the function value. So when you calculate this integration, you will have say minus 1 by 2 integral e raised to minus of 2 into 2 plus t, or say t plus 2 minus e power 0. minus 1. So this is a 1 by 2 into, I will change the integration. So I will exchange this. So this will be e raised to 0 is 1. So 1 minus e raised to minus 2t, right? E raised to minus 2 into, say, t plus 2. You can say like this. Into, that's it. So this will be the final expression. So what is your output? Let me conclude it. What is your output? What can you write about your output? Your output will be 0, right? When t is less than, what was our value? Minus 2. When t is less than minus 2. And your output will be this one. Say 1 minus e raised to minus 2 into t plus 2 by 2. When t is greater than minus 2. So this is the actual output. So this is how you can graphically solve convolution. I will just recollect it once again. So you have to convert everything into, first step is you have to convert everything into the tau axis, x of tau. Then you have to plot x of tau and h of t minus tau. Converting into tau axis will give you x of tau and h of tau. Then you have to plot x of tau and h of t minus tau. Now you have to slide h of t minus tau over x of tau. And you have to identify the different conditions where the product changes, and in that margin you have to calculate the convolution integral, that is minus infinity to plus infinity product of the waveforms d tau. Product of the waveform means x of tau and h of t minus tau. So that's all about continuous domain convolution. We call it as convolution integral. Thank you.